So I'm going to speak about, I guess something that is complementary to what Paul presented. He actually presented some pieces of it, which is has to do with melting at the bottom of the mantle and the effect it has on the long-term evolution of the Earth. So just to acknowledge my co-workers, in fact, Paul is one of them. We published recently a paper on something similar to that with Martina Uvrova, and John Handlund from Berkeley, and Nicolas Colty is the co-worker, so I guess he won't be too mean to me after that. So before, I would like to first introduce the whole problem of the thermal evolution of the Earth. It's a long-standing problem in geodynamics. It's sometimes termed the paradox, like a low Urey number paradox. The Urey number essentially is the ratio of heat production by radioactivity and the radiogenic heating to heat loss of the Earth. And at the present time, this is, I'd say, pretty much well constrained to be less than 50. I mean, that means like less than 50% of the heat flow at the surface comes from radiogenic heating. I won't go into the details of how we know that, but that's, I guess now there's maybe a consensus on that. And then, so starting, essentially, the way you do it is by writing down an energy equation for the whole Earth. I mean, that's a standard way to do it, to say that the internal energy of the Earth evolves due to heat production and heat loss, and the balance between the two will tell you how you evolve when you go back in time. And okay, heat production, it's easy. You ask a geochemist how much there is, and then you can compute backward in time from the present time. Of course, you don't want to have too many geochemists because you would have too many different answers, but if you have only one, that's fine. I'm saying that for the geochemists in the room so they can hassle me with that. Anyway, then there is a question of how does the heat flow at the surface evolve with time, or more precisely with the temperature of the Earth. And standard scaling laws for heat transfer by convection essentially predict that the heat flow changes with the internal temperature of the planet as a power of 4/3 times the viscosity at the power of -1/3. And the viscosity, we heard about it a lot already, depends strongly on temperature. So if you start from the present time here and you go backward in time, you see that the heat loss is much larger than the heat production. So when you go back in time, of course, this equation predicts that the Earth was warmer before. Of course, the radioactivity was larger as well, but because of this very strong temperature dependence of the heat flow, when you go back in time, you increase the imbalance between heat production and heat loss. And so very rapidly, when you play this game, you end up with the Earth being entirely molten, maybe a billion years ago or something like that. So that's the basic idea behind this problem. There's been several ways of solving that problem. One that was first proposed by Christensen in 1985 was to say, well, maybe this heat flow law it doesn't work for the Earth's mantle, and in particular, this exponent here may not be 1/3 after all. It could be, say, beta, and then you would have 1 plus beta here, and then you can play the same game exactly. So here it's shown the temperature of the mantle and the heat flow as function of time when you go backward from the present situation. And these the two numbers here are the present time Urey number that is allowed to have something reasonable in terms of long-term evolution. That's for like the classical 1/3 value here, and you see that the Urey number is very, very well constrained in this kind of model to be very high compared to what we think it is at the present time. One way around that is to actually decrease the value of this exponent, because then you decrease the feedback of the temperature of the mantle on the heat flow by decreasing the effect of the temperature dependence of viscosity. So in fact, if you go to quite low values of this exponent beta, then you could have a Urey number that is much more reasonable in terms of long-term, that is compatible with geochemistry and that gives you long-term evolution that is reasonable. The problem is that so far there's absolutely no self-consistent dynamical model that gives such low values of the exponent beta. So it's still a pending question. One alternative scenario that I'm going to talk about is to actually go back to this equation and maybe change it. Essentially, when you use an equation like that to solve the thermal evolution problem, you essentially assume that the temperature of the mantle essentially is enough to define completely what is the energy of the Earth. Essentially, what this means is that you have only one temperature and that the core and the mantle evolve at the same pace, okay? Which is a very strong assumption, in fact. If you instead say, okay, now we have two equations, one for the mantle and one for the core, with the CMB heat flow that comes in between the two, then of course, when you go back in time, you have the heat flow at CMB that depends also on mantle temperature, but the heat flow, the temperature of the core does not feed back on the heat flow across the mantle, okay, because the temperature of the core does not affect at first order the viscosity of the mantle, okay? Of course, the temperature of the mantle is in between the two, so if you increase too much the temperature of the core, maybe you increase also the temperature of the mantle, but the feedback is completely different. And so instead of saying when you go back in time that the mantle was, or the whole Earth was much warmer, you could say that the mantle was just slightly warmer and the core was much hotter. And by that, by doing that, you can actually cut the feedback loop. There are actually some arguments to say that the core has cooled much more than the mantle. The mantle cooling over 4.5 billion years is actually quite constrained by the phase diagrams of the mantle, and that's from a paper by Abe on the long-term evolution on the crystallization of a magma ocean just after the formation of the Earth. And essentially, classical ideas about formation of the Earth is that it was, at the beginning, there was a phase called magma ocean where everything was molten. Then you expect to have temperature in the liquid to follow an isentrope and decreasing with time until you get at the surface to a temperature where you have 40% or say 50% solid and 50% liquid. At this stage, you transition from magma ocean to solid state convection. And this is at a temperature which is essentially 200 degrees more than the present time. And it takes about 10 million years to get there from a completely molten Earth. So this means that 4.5 billion years ago, the temperature of the upper mantle was no more than about 200 degrees more than the present time. Okay? On the other hand, for the core, and I'm going to elaborate on that, and this is a plot that we already saw this morning, there are some arguments to say that the heat flow at the CMB is actually quite large, and this implies a large cooling of the core, and I'm going to elaborate on that, and essentially the core has cooled more probably than this kind of figure here. Just so I'm going to right now elaborate on that. Already Paul mentioned the fact that the CMB heat flow has to be above some value to be able to maintain a dynamo in the Earth. We know that the Earth has had a magnetic field for at least 3.5 billion years, or maybe 3.2 billion years, but that's a long time anyway. So you can drive the dynamo at present by a combination of thermal convection because you cool from above, and also compositional convection because you crystallize an inner core that is iron-rich, and so you release some light elements at the bottom of the core, which can drive compositional convection. Before the inner core, of course, you don't have that. Then you have only compositional thermal convection to drive the dynamo. And this means that to make the same kind of heat flow, you need a larger heat flow before the inner core existed. So you can kind of factor these constraints into a thermal evolution model to use the existence of a magnetic field as a diagnostic for your thermal evolution. These criteria depends quantitatively on the actual heat flow at the CMB, of course, and the thermal conductivity of the core, because in the core the temperature follows an isentrope, and all the heat that is conducted down this isentrope is not available to drive the dynamo. It's not something that will help make motion. So if you have, essentially what this means is that if you have too much, the thermal conductivity that is too high, you would transfer heat without convection. You would transfer heat by conduction only. And the thing is that recently there's been several studies, and including one in which I'm a part of, who re-evaluated this conductivity of the core to much higher values than previously thought. Essentially, values like 85, more than 85 watt per meter per Kelvin at the CMB, which compared to the mantle that we talked about this morning, it's about 10 times what the lower mantle, the conductivity at the bottom of the mantle is. And it increases very strongly with depth, so you have like 150 at the bottom at the inner core boundary. If you take this temperature and you multiply by the isentropic temperature gradient that you expect for a fully convecting core, then you have a heat flow along the isentrope, which is in this kind of figure here, which is 70 milliwatt per meter squared, which is similar to what people think comes out of the core at the present time. And moreover, there is a maximum value at mid-depth in the core. And this actually, from this you can compute energy balances in the core, and you can predict that for a CMB heat flow, for example, of 10 terawatt at the CMB, it's quite a large value already, you have a layer at intermediate depths in the core where the convective heat flow is negative. That means you would tend to stratify the core in this region here. And you can compute for different values of the heat flow at the CMB, the region that is stratified and the region that would be convecting. And if you, from this kind of conductivity, if you take the heat flow at the CMB to be exactly equal to the heat flow along the isentrope, it's not enough to maintain convection at the top of the core. And essentially, you would have a layer about 1,500 kilometers thick that would be stratified at the top of the core, which I'm sure we would have seen from different methods, seismically or from geodynamo. So what this means is that the heat flow must be actually larger than this value, even at present time. Okay, the actual heat flow at the CMB. So that gives us some constraints of what should be the minimum value of the heat flow at the CMB, and that's, this is typically about 10 terawatts. Okay. And then you can compute the thermal evolution of the core with this minimum, the most conservative thermal evolution of the core with this minimum requirement to maintain the dynamo. And depending on the on the present time value at the CMB, which depends on the kind of composition you assume for the core, and the minimum is here 85, but typically you get for the initial CMB temperature, you get something that is some 700 Kelvin more than the present time value, and so that's how I get the number I just showed you before. And the inner core is also very young. If you go from the present time, essentially that puts you at the CMB initially at this temperature here, which you can compare to recently published melting temperature of Mantle minerals for different compositions, and essentially that puts you right in the middle of all these estimates. Anyway, it will be whatever the uncertainties, etc. It's higher than the solidus, that's for sure. So it means initially the core must have the lowermost mantle must have a significant fraction of partial melting. In fact, there are presently evidence of partially molten regions at the bottom of the mantle, so it's not actually a big surprise that when you go back in time, there must have been more. It's a very highly debated issue. I think maybe Sebastian Ross, that is going to speak tomorrow, will show a bit more about this. These are plots from him. This is typically, this is one of these studies that looked at these ultra-low velocity zones that we already mentioned. This is a tiny region here. This square here is this at the CMB, so it's about 100 kilometers across. And this is the only region where the seismologists see this specific feature that are termed ULVZ. We don't see them everywhere. I guess they are seen in these red regions. They correlate somehow with the the edges of the large low shear wave velocities provinces, the LLSVPs. So that suggests a link. There are regions. The blue regions here are regions where we don't see the ULVZs. So in fact, there are places where there are data, and these data don't show any sign of these ULVZs. So these regions, it's not a uniform feature. It's a patchy feature. And what are these ULVZs? Just to kind of sum up what seismologists find is a delta VP of about minus 10%, which is a big number compared to the kind of number that we discussed before on the kind of large-scale velocity variations. If you compare with here, for example, the tomography map is between -3 and +3. Here, that's for VS, of course. And so for VS, you get minus 30% in ULVZs, so that's a very big number. Also, it seems to be a high density. These are high density regions of a thickness of about a few tenths of kilometers. There's been two interpretations of that. I guess the earliest one was a partial melt, and I'm going to speak a bit more about that. And also, it was recently proposed that it could be actually solid, but Fe-rich solid. In any way, any case, you need lateral variations of composition to make patchy ULVZs in these things. The interpretations in terms of solid is essentially, that's one of these recent papers on this. This is velocity measurements as function of pressure for the composition that is very iron rich here, okay? And so by mixing this kind of composition with about 10% of this very iron rich composition with normal mantle, then you can match the VP and VS reduction in ULVZ in the solid state. Okay, that's the main argument here in this paper. The problem is, of course, how do you make these such very high Fe-rich, highly enriched iron patches in the first place? Probably, the best way to do it is actually by fractional crystallization. And also the question is, would this kind of material be still solid at the condition of the CMB? And it's not clear at all. For example, in this paper, the authors looked at the melting of wustite, and if you extrapolate this curve to the CMB condition, you get a value that is typically the kind of value of the CMB temperature at the present time. So probably this kind of composition would actually be a liquid at the condition of the CMB. So we want to also match the density and look at what the temperature should be there. These are from two recent papers. This is a comparison of the different melting temperature, liquidus and solidus, that has been reported in the literature, compared to the present time CMB temperature range that is in this row here. What you take from this kind of plot is that to have liquid or partial melt at the CMB in the present time, you need to be at the top of this kind of range, or you need to change the composition and put more iron in this region to actually decrease that temperature to lower values. Okay. In terms of density, also you need to mix if you want to match the density that I just discussed from Sebastian Rost. Is that if you need to mix normal mantle with something that is much more iron-rich over there, okay? Of course, this number is not that well constrained, the actual ULVZ density, but there are some constraints, and we need to use them. In addition, so this means that ULVZs must be rich in iron compared to normal mantle, but since also there are very tiny patches, maybe not like a big chunk of stuff. So this means also that there must be in equilibrium, and particularly if it's liquid, if it's partial melting, it should be in equilibrium with the surrounding. So the big LLSVPs must be also rich in iron, although less than the ULVZs. So this is the kind of cartoon that Ed Garnero produces on a daily basis, and so. Here we go. So we have these piles and the ULVZs at the bottom of that. And the best way to form these kind of things, enriched in iron, and is to actually have I mean, that's at least one way, is to have fractional crystallization, which is what we proposed some years ago. I'm going to drop that because I'm running a bit short on time. So recently we've been producing a model, developing a model where we couple the thermal evolution of the solid mantle to get back to the long-term evolution, where the behavior of the heat transfer behavior is actually quite similar to the standard, usual, old school thermal evolution model in terms of scaling laws. But we take into account the fact that there is a freezing of a layer over time, and the liquidus here changes with time because of pressure, but also because of composition. And so actually the liquidus stays almost constant. So essentially the heat flow can stay rather constant in this kind of model. And this is coupled to the basal mag motion and the core. And so with that, starting from an almost zero thickness of melt, now we go back to something like 1,000 kilometer thick basal magma ocean in the early Earth. And we do that with heat flow at the surface, which is almost constant, while the heat flow at the bottom of the solid mantle and the heat flow at the core mantle boundary changes much more with time. Okay. And these are the different energy terms in the balances. The key thing here to look at here is the fact that the heat flow at the core mantle boundary is actually is here and is actually over the minimum value for dynamo, barely above, so it's not very satisfying, but still we can make a dynamo run for 3.5 billion years. So just to wrap up on these things, I want to just discuss a bit about the formation of this basal magma ocean. Early on, originally we proposed that we crystallize from the center of the mantle, the basal magma ocean, because the liquid at the bottom of the mantle would be denser because it is richer in iron than the solid. There's been two recent papers that looked at the partition coefficient between liquid and solid at the lower mantle pressure, and they are completely different. The results are completely different. I'm not sure which one is right. There are, this is the study by Denis Andro, and I'm sure I'm going to talk about that later. They find that the iron indeed partition preferentially in the liquid, but not much more compared to this paper where they find a much larger partitioning of iron in the liquid. I want to mention that the way it is done is by computing the composition in this kind of area here, and so there's the resolution is not completely, it's not great, so there might be an issue here. Plus, it's not so clear. Also, the temperature gradients are very big, so there might be Sorey diffusion. In the experiment by Nomura and others, they do very short heating to avoid Sorey diffusion, and the resolution have much higher. The images have much higher resolution, so that might be something to discuss. To end up, in this paper, they also computed the density of magnesium perovskite compared to the liquid at CMB pressure, and they find, depending on the composition that they use, in both cases, in fact, in both composition here, they find that the magnesium perovskite that crystallizes from at the bottom of the mantle from such magmas would actually sink, would be denser than the liquid. So that would go against our scenario, okay? But of course, if you start by crystallizing magnesium perovskite here, you take out essentially the magnesium perovskite end member from the liquid, then you enrich the liquid in iron compared to the solid. So actually, the liquid would evolve in such a case. The liquid would evolve in this direction, where it would actually become denser than the solid. So you can come up with a different scenario where you start from a full magma ocean and you start by crystallizing at the bottom. And as fractional crystallization proceeds, the liquid becomes denser, becomes richer in iron, and at some point can become denser than the solid below it, and so you could have relative instability that could lead to an overturn, and that could make this basal magma ocean. Anyway, fractional crystallization in any of these systems will clearly have dramatic effect on many things in terms of dynamics, and would set the initial condition for the long-term evolution of the Earth. And of course, it will have also effects on a lot of geochemical observations that we haven't modeled in this thing here. So to conclude, we can reconcile the long-term evolution of the Earth with classical scaling laws for mantle convection if we include melting in the lowermost mantle for the early Earth, and much more cooling in the core than in the upper mantle. Essentially, we still have to work out what is the correct scenario for making this basal magma ocean in the early Earth, but this can hopefully be done in the near future, because there are more and more data from mineral physics on the phase diagram. So I let it here.